Alright guys, welcome to this page of the notes. Let's go ahead and continue with this idea where we are proving that two triangles are similar using our new similarity theorems. Let's see what we can do with this next example problem. Remember, we have the angle-angle similarity theorem. We have the side-angle-side similarity theorem. But in both of those theorems, I need to know something about angles. And if you take a quick look at this diagram, hopefully you quickly recognize I tell you nothing about angles. So that's not going to work. Aha! Fortunately, I have that side-side-side similarity theorem. I think that one's going to be my winner. So here we go. Side, side, side. Let's see what happens. JH corresponds with MN. Make sure we keep these in the same order, so I'll do the longer side divided by the shorter one. So MN over JH. What's my next one? Well, it looks like my next one is GH, and that's going to correspond with ML. So longer side over the shorter side, so ML over HG. And then finally, I just left with two sides, so GJLN. So we have LN over JG. Alright guys, plug and chug. With any luck, they'll all come out to be the same, and we will have proven that these two figures are similar. Let's find out. I have 15 over 10. I can divide both of those by 5, and it'll leave me with 3/2. ML. Well, ML is 12. GH is 8. I can pull out a 4. Ooh, leaves me with 3/2. So far, so good. I just need this last one to come out to 3/2, and cuckoo ka-choo, we got ourselves a winner. LN is 6, 4, divide both by 2, boom, 3/2, and there we go. The ratios are all the same. That means my scale factor is 3/2, and yes, these figures are similar. Side, side, side. Similarity theorem. Perfect. Hey, let's do another one. Alright, once again, I've given you two figures. I want you to determine whether the triangles are similar. Got to be able to justify your answer. Ooh, look at what I've got here. I have an angle, I'm given an angle, and it would appear that I'm given information about two of the sides. So here's what we're hoping for. We're hoping for side, angle, side. Okay, well, I know that CA, not black, different color, red. I know that AC or CA, whatever, corresponds with FH or HF. So there we go. I have AC over FH, which is going to be 10 over 5, which is 2. Awesome. I have BC and GH. I need to do BC over GH, which is going to be 6 over 3. Awesome. Again, I wind up with 2. So I now have two corresponding sides that both have the exact same ratio, 2 and 2. My scale factor is 2. Now, remember the way the theorem works. It is side, angle, side. Since these are my two sides, it must be an included angle. And so I go to my diagram. I need angle C to be congruent to angle H. Do I know that? No. They tell me that angle A is congruent to angle F. Is that helpful? It is not. Please be very, very careful. The way that the side-angle-side similarity theorem works is that whatever two sides you use, it must be the angle that is included between those two sides. There is no side-side angle similarity theorem. There isn't one. It's side, angle, side. I must know. I would need to know that angle C is congruent to angle H. But since I don't know that, I cannot prove that these triangles are similar. So, for those of you who are working or taking this class with me, please do not just assume that because I give you one of these questions that you can prove the triangles are similar. It is absolutely possible that I will give you two figures and I do not give you the correct information for proving one of our similarity theorems. First, you need to either know two corresponding angles, or you need to know all three sides, or you need to know side, angle, side, where that angle is the included angle. If it's not the included angle, you don't have enough information. They may be similar. It's totally possible that C is congruent to H, but I don't tell you that and you don't have any way to prove it. So you're done. Two more questions for you here just to sort of wrap things up and bring this chapter here full circle. What I want to know is, are all isosceles right triangles similar? Explain why or why not. Well, remember, with an isosceles right triangle, an isosceles triangle has two sides that are the exact same length. And then, of course, an isosceles right triangle means that the isosceles triangle has a right angle in it. Let me draw a couple for you. Let's say that this is one of my right isosceles triangles because I have x and x, right? Both of those sides have to be the same. That's what makes it isosceles, and it has a right angle. Let me give you another one that's a little bit bigger. Ooh, nice. There's a right angle. This is side y and side y. Once again, I have an isosceles triangle because, right, both of these sides have the same measure. That's what makes it isosceles. It's an isosceles right triangle because there's my right angle. Well, in order to prove that these guys are similar, I need a side, angle, side. Well, okay, awesome. I have corresponding sides, which are going to be y over x, right? Y divided by x. Just set up the ratio. Do I have a corresponding angle? Sure I do. They're both 90 degrees. 90 is equal to 90. Ooh, we're getting close. I just need one more side. Well, here's corresponding sides there and there. Do the longer side divided by the shorter side, y and x. Y over x. And sure enough, the side-angle-side theorem proves. I am going to run out of space, but here's what it proves. The side-angle-side theorem proves that all isosceles right triangles are similar. They have to be. Why? Because you already have two sides that are the same, right? With a right angle in between. And then in the other isosceles triangle, right, these two sides have to be the same and a right angle. And so what you're going to be able to do is you'll always be able to set up the ratios that are the same ratio. They're equal, they're proportional, and you're always going to have a similar angle because it's a right isosceles triangle. So hopefully that one's pretty easy to answer. The next one, okay, so we have an angle-angle similarity theorem. We have a side-side-side similarity theorem. We have a side-angle-side similarity theorem. It's a great question. Why isn't there an angle-side-angle similarity theorem? Well, here's the answer. That's too much work. Angle, side, angle is too much work. What do you mean it's too much work? Well, here's what I mean. We already said that we have an angle-angle similarity theorem. If you can prove that two corresponding angles are congruent in two different triangles, you know that's enough. Angle-angle. Just prove two corresponding angles are congruent. You know the triangles are similar. So then why would you do the extra work of proving that an included side is also similar? That's doing work you don't have to do. all you got to do is show that two angles are similar, and that's good enough. By doing an extra side, you're just doing more work that you don't have to do. So the reason there isn't an angle-side-angle similarity theorem isn't because it's not possible. Sure, it's possible. It's just more work than I want to do. If I only have to do two things instead of three things, I'm going to do two things instead of three things, and hopefully you'll work the exact same way. So the reason there's no angle-side-angle, because proving that two corresponding angles are congruent is more than enough. That's all we need. Alright guys, what we've done so far here in this chapter is we've taken a look at dilations. We've looked at how do you perform the transformation of a dilation by doing sequences of similar transformations. We then went back and looked at you guys proving that figures are similar using our similarity theorems, and then once you know they're similar, setting up those proportions or setting those angles congruent so that you can then solve an algebra problem. I had a great time taking a look at similar figures with you guys, and I'll see you next time.